Hello friends, welcome to the mathematical room. I am the caretaker. So today we are going to start ring theory. But before that we need some prerequisites, and the prerequisites that we will look at today are the integers. Now in this part we are going to have a look at the basic algebraic and number theoretic aspects of the system of integers, and this is actually the third section of the first chapter from Herstein's topics in algebra. So here we are not really concerned about the axiomatic development of the system of integers. So it's not like what we did with the natural numbers in the previous videos, although we will look at the axiomatic treatment of integers, but that is a separate thing and that will go alongside this development of integers. Now here, instead of going axiomatically, we are going to assume that we already know many of the basic properties of integers and we are familiar with many of the facts like the Euclidean algorithm, the principle of mathematical induction, in the context of, that we have already seen previously. And also we will look at the well ordering principle. So the Euclidean algorithm in the context of integers looks somewhat like what we have already seen for the natural numbers, but here the objects are integers, okay, which include the natural numbers, as you already know. So it goes like this: if a and b are integers with b non-zero, then there exist unique integers q and r such that a is equal to qb plus r and r satisfies these inequalities. Now here you can see that since b is a non-zero integer, it's possible for b to have negative values. Because of that, we are using absolute value of b here. Okay, so this is what the Euclidean algorithm is in the context of integers. And the well ordering principle, which we will use quite often in this development or in this study, is like this. And it just says any non-empty subset of the set of natural numbers has a least element. Okay, now so this one says that if we have a non-empty subset of the set of natural numbers, then that subset will have a least element. So what it says is this, that if I have, okay, by the way, in Herstein's topics in algebra, natural numbers don't include 0. So it's not like the natural numbers that we have developed in the previous videos where 0 is included. Herstein does not consider 0 to be a natural number. But as I have already said, this is simply a matter of convenience. So whether you call 0 a natural number or not, it's up to you, and it does not change the mathematics. But you have to be careful that when you are looking at the words natural numbers, it should be certain what meaning is attached to them. Okay, so the thing that we are doing now, for us 0 is not a natural number. Okay, so we will go according to how Herstein goes. So what this means is this, or more properly or more specifically, this can be restated like this: any nonempty subset of the set of all positive integers has a list element. So if A is a subset of the set of positive integers, the set of positive integers can be denoted by this symbol. Blackboard bold Z suffix plus. Okay, and here one more thing must be mentioned about the set theoretic notations that Herstein uses. The notation that we have so far used in naive set theory, which denotes inclusion, is this. By this we mean the fact that A is a subset of B. If A is a proper subset of B, for that we write this notation. However, for Herstein, this same thing Herstein will write like this. For him, this means that A is a subset of B. If he wants to say A is a proper subset of B, he will just simply write like this. Okay. So in this book, we are going to use these notations. Note one more thing. This is different from this. It says that A is not a subset of B. This one says that A is a subset of B, but it's a proper subset of B. That is, there is at least one element in B which is not in A. So with these notational things out of our way, we now understand this relation. It says that A is a subset of the set of positive integers, or in Herstein's treatment, a subset of the set of natural numbers, and it's non-empty. It's non-empty. Then there exists an element A in A such that A is less than or equal to B for all B belonging to A. So this A is the least element of A. So any such non-empty subset of Z plus will have a least element. That's what well-ordering principle is. Now the logical development that we have been following, or we have decided to follow from the previous videos, where we have constructed the system of natural numbers, and using those things we will develop the integers, and then we will come across these properties. So from that point of view, these things actually can be proven, okay? The well-ordering principle can be proven, and in fact, the Euclidean algorithm can also be proven. In fact, we have proven it already in the previous videos in the context of natural numbers. But now that we have integers, so this is a result that is still unproved for us. We will prove this, but in our study of elementary number theory. there we will see the proof. For now, we assume that this result, the Euclidean algorithm in the context of integers and the well-ordering principle are given to us. So when we state that we are going to assume that we know many things about the system of integers, these are some of the things that we are supposed to know. Okay. Now, in in the Euclidean algorithm, there is a special case that, as you may already know, if r is equal to 0, if in this situation r becomes 0, r can be 0, there is a possibility, then a is equal to qb, right? We say, so this prompts us a definition. This prompts a definition. We say a is divisible by b not equal to 0 if a is equal to qb for some integer q. Okay, for some integer q. So if the remainder is 0, then we say that a is divisible by b. Also note that we are dealing with integers. A and b are integers, q is an integer. Right. In this case, we also say b divides a. If a is divisible by b, then b divides a. They mean the same thing. And we write b followed by a vertical column followed by a. This symbol means the fact that b divides a, to denote this fact. If b divides a, we say b is a divisor of a and a is a multiple of b. Okay, so these are some terminologies related to divisibility, the relation of divisibility. If this happens, then we say that b is a divisor of a and at the same time a is a multiple of b. If b does not divide a, we write like this. So we strike the vertical column out, the vertical bar out. Okay, so these are some of the notations and the concept of divisibility which arises as a special case of the Euclidean algorithm. Now we look at some elementary properties of this relation of divisibility. Some of them are quite easy, but slowly we will move on to the more advanced properties. So the first few are like this. Oh, by the way, to simplify things, let's just make this assumption. To avoid saying that something is an integer, since This whole thing is about integers, this whole study right now. So we will have occasions to use the word integer very often. So we try to simplify that usage. Something is an integer. Again and again, we make the assumption that any symbol in this section means in the third section of the first chapter of Herstein's algebra. In this section, any symbol written as a lowercase Latin letter will denote an integer. Okay. So, for example, here A is divisible by B. When we say things like that, we know from this assumption that A and B are integers. Note one more thing carefully, that the divisor by definition is never 0. Okay, that's because division by 0 cannot be conveniently defined in the majority of mathematics. So we avoid that situation. Also, although there are some situations where division by 0 is permitted, but those places are rather special. We will come across them, say for example in extended real number system, but that's a long way from us. That's still, it will take some time to get to that. So for now, division by 0 is not there, and we make sure that whenever we divide an integer by some other integer, that other integer must be non-zero. One more thing is that because of that, when we look at a symbol like this, it's assumed that the divisor is non-zero. Otherwise, this symbol is meaningless, because the symbol has been defined in the context of divisibility, and that includes this condition. So the divisor cannot be 0. So we note an integer. Okay, now so with all these things out of our way, we are now going to state some very simple consequences of this definition of divisibility. So this is a result, a small observation, we can say. If A divides 1, then A is either plus 1 or minus 1. The proof of this is very easy, and I leave it to you. Okay. The next property says that if A divides B, see here this symbol automatically means that A is non-zero, because A is the divisor. Just like that, if A divides B and B divides A, so these two conditions ensure, among other things, that both A and B are non-zero, because they are divisors in two situations. Then A is equal to plus or minus B. So these are very basic observations about the divisibility definition. If A divides B and A divides C, then A divides MB plus NC for every integer M and N. Okay, now these results appear as actual exercises at the end of this section. So we are going to solve them. Now they appear like this. So they appear like these exercises. So the first exercise exercise 1. So unlike Tau's notes, Herstein has not bothered to number the exercises according to where they are appearing. For example, these exercises appear at the end of this section. So according to that scheme, if he wished to use the section number, this should have been exercise 131. First exercise of section 1.3, but it chooses not to do so. So we will also follow that. It does not really matter if A divides B, and this one I think is given in the same way, exactly like this. A divides B and B divides A. Show that A is plus or minus B. So the solution goes like this. Since A divides B and B divides A, so by definition of divisibility, there exist integers, but I have decided not to write the word integer. So there exist m and n. So these are integers such that A divides B means B is m times A, and B divides A means A is n times B. So this implies, what does this imply? If I use the expression for A here in this equation, then I get B is equal to m n B. So in place of A, I have NB. Now, by cancelling B from both sides, we get 1 is equal to mn. Now here I should justify what is this cancellation law. You see, we have already obtained one cancellation law while dealing with the natural numbers. Now here also we will have a cancellation law. The previous one looked like this. If A plus B is equal to A plus C, where A, B and C are natural numbers, then this will imply B is equal to C. We have in fact proved this. So when we axiomatically treat the integers and prove all its properties, there also a cancellation law will appear in the form, that involves multiplication. Here also I think, yes, why am I writing addition? I have come across a cancellation law which involves multiplication and an additional condition that A must be non-zero. These are natural numbers. Then I can write B is equal to C. And this cancellation law does not involve any concept of division in its proof, as we have already seen in the previous video. So, just like that, when these are integers instead of natural numbers, There's also a cancellation law that involves multiplication. So we have used that one here. And why is that possible? Because you see, B is dividing A, so B is a divisor. So by the definition of divisibility, B has to be non-zero. So I can cancel B from both sides to get 1 is equal to Mn. Okay. Now if we look at the last equation, 1 is equal to Mn, where M and N are both integers, what does this tell me? But this gives me, or this gives us, the fact that M divides 1. N also divides 1, but we need to look at only one of them. N divides 1. So, by this result, whose proof I have left to you, M is plus or minus 1. Now you use this information here. Hence, B is, M is plus or minus 1, so B is plus or minus A, or A is plus or minus B. When A is plus A, when B is plus A, then A is plus B. If B is minus A, then A is minus B. So we get this. So this one we have proved. So just like that, there is another exercise which deals with this property. This is exercise 2. Some of these are admittedly very easy to solve, but since I have decided to not leave any exercise unsolved other than the extremely trivial ones, so I will solve all of them. As many as I can. So now, exercise 2 asks if B is a divisor of G and of H. So I have written what is exactly given in the question, in the exercise question. Show that it is a divisor show that it is a divisor of Mg plus Nh for all M and N that we can add. So its proof also starts in much the same way as the previous solution, its solution. So from A dividing, okay, so we now have G and H, and we don't have A, we have B. From B dividing G and B dividing H, we get G is equal to Bk, comma, H is equal to Bl for some integers K and L. Hence, so we now have to show that B divides Mg plus Nh. So we will take the expression Mg plus Nh. So substituting for the expressions for G and H, we get Mbk plus Nbl. So B can be taken common out. So this becomes Mk plus Nl times B. Now you look at this equation. mg plus nh turns out to be b times an integer, and mk plus nl is an integer because m, k, n and l, these are all integers. So using the fact that addition and multiplication of integers are again integers, we can conclude that this is an integer. So this implies b divides mg plus nh. So this completes the solution to the second exercise. Okay, now we come to the important definition of the greatest common divisor. So we take the definition. Now just like the exercises, Herstein has not bothered to number the definitions at all. He just simply writes definition and that's all. The positive integer C is said to be a greatest common divisor of two integers a and b if the following two conditions are satisfied. See, although I have said that I will not write the word integer, but sometimes I have to write positive integer. Okay, so in those times I will write the word integer, positive integer. I can write positive c also, but if I suppress the word integer altogether, things may become confusing at some point. Because when we already know what real numbers are, complex numbers are. So if we just simply see positive c, inadvertently we may have the idea in our mind that c is a positive real number. That sort of mistake happens. So that's why I write positive integer. So in such places where I need to say explicitly the sign of the integer, I will use the word integer. So c is a positive integer, and such an integer is said to be a greatest common divisor of a and b if 1. C divides a and c divides b, and 2. If d divides a and d divides b, then d divides c. So what this definition says, a and b are two given integers. A positive integer c is said to be a greatest common divisor of a and b if c divides both a and b and it divides any integer that also divides both a and b. So if d divides both a and b, then I have said the opposite thing. It is divisible by any integer that divides both a and b. Then such an integer c is said to be a greatest common divisor of a and b. Now the definition, the way it shows itself, it's not immediately obvious from the definition that if a and b are arbitrarily given to us, that they will have such an integer c for them. That is, their greatest common divisor will exist. So this question has to be addressed and it has to be proved. Now, before we go to those things, there are some points. And in fact, one point is the use of this article a. Generally, in definitions like this, we see b. There is only one such positive integer satisfying these conditions. but the way the definition has been given, it may seem that whenever a greatest common divisor of A and B exists, it may be the case that there are many. We will now show that that is not the case. If A and B has some greatest common divisor, that is the only one. So any two integers have at most one greatest common divisor. So let's just look at that. And it's not very difficult also. Let me just assume A and B have some greatest common divisor. Okay, to shorten that, I can call it GCD. Have some GCD. So let C1 and C2 be GCDs of A and B. Two possible greatest common divisors. Our aim is to prove that they are actually equal. Now, considering